All right, section 1.2.3, creating exponential equations. So in the last two sections, last time we talked about creating linears, right? Linears was y equals mx plus b. Y equals mx plus b. And we talked about linear inequalities as well, and how those two tie together. If you recall, m stood for slope, b stood for the y-intercept, right? Or m was the coefficient, b was the constant, right? We ended up with things that looked like this, and then we would solve them to find an answer. We usually end up either finding y or finding x. Today we're just going to do something slightly different. It's a little bit more on the logic side, okay? So we're going to start with exponentials. This is the general form for an exponential, y equals ab to the x. We've seen this once or twice, not too much, but we have seen it. We're really going to break it down today and what it talks about. We've graphed these. We know that they kind of look curvy, right? They look like that. We've seen how the exponent rules play into these, but we're going to really dive into what these pieces mean. So in this general form, each one of those four variables actually has a different definition. So here, only two of them really meant something, and then x and y kind of like it depended on the problem. Here, though, all four of them have a very specific definition. A is going to be your initial amount. B is going to be your rate. X is your time, or your time period, and we're going to see that sometimes this needs to get adjusted. And then y is going to be your final amount. Final amount. So each one of these has a very specific breakdown. A is always what you start with, right? In the case of Javier and his banking account, right? We had Javier put in $750. There was a rate of 3%, right? So we had to say it was 103. We had to adjust that a little bit. So B, you may have to adjust. And then X was per year, luckily it was per year, so it's time period, we put in 5 years. But you'll see that you might also have to adjust that one, we'll see that in just a sec. And we got out a number of $896 or something like that for his final amount. So that's how these always break down. Initial amount times the rate to the time period equals the final amount. That's what it breaks down to. And it's not always about money. It could be about population, could be about a whole bunch of other stuff. But basically it's the same idea. The initial amount, the rate, the time, and the final amount. You may see them represented slightly differently. You may see some other ones that look like, I don't know, y equals a times 1 plus r to the t. Sometimes you see that where, just notice that 1 plus r part is just the b, t is just the x. So it's the same thing. It's just it's trying to help you out with that 100% thing we had with Javier. You may also see it even more broken down. This is the one the bank uses. Principal sounds your starting amount, so A. It's 1 plus or minus r over n to the nt. That's a really broken down one for you to help with your bank account stuff with interest and whatnot, like a loan or a bank account, interest for savings, things like that. Really, really broken down. The n represents months. We'll get into all that and what other forms you might see, but basically right now the one you want to commit to memory is a b to the x. A, b to the x, right? And it's got the same four breakdowns. And as long as you think about b and x logically and how you should slightly adjust those, you don't really need to know these other forms. They're just there to help you. You might see them, you might see how they work, but this is really the most important one. So let's try it out. Let's try a population, or let's try example 1. A population of mice quadruples every 6 months. If a mouse nest starts out with 2 mice, how many mice will there be after 2 years? Write an equation and then use it to solve the problem. Luckily, the steps for creating exponential equations are the exact same steps for creating linear equations. First, we read the problem. Check. Next, let's read it again and underline or make a list of things we know, right? So the population of mice quadruples every 6 months. And I'm actually going to underline those as two separate things. You're going to see why in a sec. If the mouse nest starts out with 2 mice, so started with 2 mice, how many mice will there be after 2 years? All right. Write an equation used to solve the problem. Let's go ahead and do that. So we know things quadruple. We know it's every 6 months. We know they started with 2. And we want to know how many after 2 years. That's the question. Okay. Now the question, before we were defining our question, always defined x, right? It was 9 times out of 10 it did anyways. Now that we actually have more set definitions for things in exponentials, let's take a look at this question. How many after 2 years? Is that asking about x? Is it asking about a time period? Not really. We know the time period, 2 years, right? So this is going to be x. However, the question is actually asking about how many after this, how many in the end. It's asking about y. So this question is actually asking about y, not x, right? So it's important to remember what each thing stands for. That way you can actually answer your question, you know which piece you're looking for. So if that's the question, we should have all the other pieces. We should have a, we should have b, and we should have x, right? Otherwise we can't answer y. So let's go ahead and try and build our equation. We'll start with just a general form, y equals ab to the x. I know it's supposed to look like that, so I'm going to pretend it does, and then I'm going to fill in the pieces I know. Alright, a stands for initial amount, starting amount. Okay, starts with 2. Good thing I wrote that down, because now it's easy to find it, right? I noticed it started with 2. So this equals 2. Cool, so far so good. Now let's so check on that one. That one was pretty easy, right? Starts with 2. Next, let's consider the rate. And the rate we may have to adjust just a little bit, but let's take a look. What does the word quadruple mean? What does it mean, quadruples? That's 4 times, right? So 4 times the amount, right? Quad is 4, so 4 times the amount. Our rate is 4 times every 6 months, but the every 6 months part, that's a time period. So that is why we indicated them separately. The quadruples tells us our rate. Looks like we didn't have to adjust that. That's fabulous. So quadruple, 4 times. There, we got A and B. Sounds good. Let's take a look at the time period now. Every 6 months. Every 6 months. Now, in this general form, this is always in months or years. It's always in one of them. Okay? So if you have something happening every 6 months, then what you want to do is adjust your months by 6. So what I'm going to do is I'm going to call it x over 6. I'm going to call it x over 6. We're going to talk about that in just a second, again, when we think about the question. But for right now, that's how I'm adjusting my time period. So we'll put a little note on the side here. This is how I adjusted to make months into 6 months. I divided it by 6. Okay, so x divided by 6. And the reason I did that, let's take a look at the question. First off, it's in 2 years. That doesn't help us. We want things to be in months. So let's say instead of x being 2 years, x is 24 months. Right? 24 months. But really think about this. How many times will they actually be quadrupling in 24 months? It's not going to be 24 times, right? Because it's not quadrupling every month. When it's quadrupling every 6 months, then it's happened how many times? Well, if I have 24 months and it quadruples every 6 months, that's going to be 4 times, right? So that's why we adjusted it that way. Notice that in order to get how many times it actually happened, we had to divide by that 6. So that's why I divided by 6 in the problem. That way I can plug in any amount of months I want, and the equation takes care of that adjustment for me. So it's kind of putting the adjustment in the equation, just like with the rate, right? I don't want to sit there and think for every single time I had to think of the rate with Javier, I had to think of 100 plus what I wanted to put in. I just changed it to 1.03. So that's all we're doing. We're just adjusting that x so that I can put in however many months I want, and it'll automatically spit out the final amount, right? So I just want to make my equation as easy as possible to use so that I don't have to do math. It does the math for me. That's what I wanted to do. All right, cool. So that's the adjustment for the time period. Now let's actually answer the question. So right now we have y, right? So let's put it in red. We don't know anything about the final amount, but we have our equation. So our general equation here is starts out with 2 quadruples every 6 months. That looks like 2 times 4 to the x over 6. Cool. Now I can answer the question. So I'll go over here and use my equation. I have y is equal to 2 times 4 to the, well, we already said that x is going to equal 24 in our situation, over 6. And just as we saw, now the equation takes this exponent, it doesn't make it happening 6 times or 24 times, it makes it happen 4 times, like we talked about. That's what's going to happen. It's going to happen 4 times. So the equation took care of that for me. I end up with 2 times, remember, exponents first, 4 to the 4th, well, 4 to the 3rd is 64, times that again is 256, and then that times 2 would be 512. Alright, so my y is equal to 512. Now I'll just translate back in like 30, not even 30 seconds, 512 mice. After 2 years, they will have 512 mice. I hope they have a big cage, right? Alright, so that's the breakdown of an exponential. Notice, it was the exact same steps. Exact same steps as linear. Underline. Pull out important information. Create an equation. Use equation to solve, translate back, right? So it's the same thing. Translate, solve, translate back. It's just with exponentials, you have to watch out for things like that. Adjusting time periods, okay? Let's try another one. Let's go try example 2. But if you have any questions about what I was writing here, what something says, any questions at all, make sure you pause the video and get them answered now. Okay, example number 2. In a sporting tournament, sporting tournaments, teams are eliminated after they lose. I hope you guys knew that. The number of teams in a tournament then decreases by half with each round. If there are 16 teams left in 3 rounds, how many teams started the tournament? So we've got this tournament going on, right? And you guys have seen these before, right? It's the bracket, March Madness bracket, right? You've seen those. Everything gets whittled down, and you eventually end up somebody winning. So what they want to know is if 16 teams were left after 3 rounds, how many started in the beginning? Let's go back and let's underline some things they mentioned. So number of teams decreases by half with each round. Decreases by half with each round, right? If there are 16 teams left, and left is very important, right? After 3 rounds, that sounds like a time period. How many teams started? Ooh, very, very important. All right, so let's make sure we get that written down. Decreases by half. Decreases by half. With each round, we'll do each round. 16 teams left. 3 rounds. I'll put a little arrow to indicate 16 teams left after 3 rounds, right? And then the question is, how many teams to start? Okay. Now again, in this scenario, we have to be careful of that question. So far we've pulled out important information. Next is to define what variable will answer our equation, right? Let's look at that very carefully. How many teams will start? How many teams started, right? Let's go back and look at our little list of stuff. A was the initial amount, B was the rate, X was the time period, and Y was the final amount. Now in the last problem, we wanted to know after 2 years how many things happened. That's why we chose Y. Here we want started. Started. That's going to be A. So A is the variable we are after. A is the variable we are after. Okay? So we should be able to have, or we should have all the parts of the equation except for A. That's what we should have. A will answer our question. So let's start with a generic y equals AB to the x, right? AB to the x. And let's think about this. So we know that A is going to be the part that we don't know, right? If we knew it, then we wouldn't have to answer the question, right? So A is going to be left as A. But let's see what else we can plug in. Let's see. Well, Y is supposed to be our final amount. What would our final amount be? See anything here that says teams left, maybe? 16 teams left. Nice. 16 teams left after 3 rounds. We'll come back to the 3 rounds part in a sec. But Y is equal to 16 here. Y is equal to 16. Decreases by half would be our rate. And since it's already a fraction, we don't have to worry about, it's not negative. Rates are never going to be negative, okay? Rates, let's put that note up here. Rates are not negative. They're either fractions or whole numbers. Okay, we never saw a negative one. If I gave you a negative one, you'd see it's no longer like an exponential equation. It actually bounces back and forth. It wouldn't be, sorry, it would be exponential, but it wouldn't be one of these. Okay, so we don't want, so it's just 1/2. Don't need to worry about the decrease part. Luckily, that's after each round, right? Not after some weird 6 months or 2 years or something like that, right? Not every other round. So it's just going to be divided by 1, which doesn't change anything, right? So this is just going to be an x. But more specifically, it's going to be a 3, right? So we're looking at the specific case of after 3 rounds. So this would be a 3. All right, and now the only variable left is a, so we can solve for it. Sweet. Alrighty, let's do that. So we translated. Yay, go us. I'm going to use blue. Let's use orange. So now I've got 16 is equal to a. Let's see, what is 1/2 to the third? Well, by the exponent property, that's 1 to the third over 2 to the third. Right? 1 to the third over 2 to the third. Or in other words, 1/8. Right? That's going to be the same thing as 16 is equal to a over 8. Right? Remember, you can totally do that. Put the a on top. And then that tells me I should times by 8 to both sides. Cancel. I end up with 8 times 16, or 128 is equal to a. There, I have solved. 128 is equal to a. Now I can translate back real fast. That means that there were 128 teams to start. Teams that started. 128 teams that started. Awesome. And that's how you solve it. So it's not always are we looking for y, right? Not always is it going to be a spit out of equation. Sometimes you have to, solve for a, or even solve for b, or solve for x, or solve for y. So whatever variable you need comes right out of the question. So if you remember what they stand for, then it's very easy to figure out which one you need. If that's the one you need, you should find everything else, right? You should be able to find everything else. All right, cool. Any questions, you can stop the video. Okay. Let's do the next one together, and then I'll have you do number 4 by yourself. So let's try the next one together. The population of a small town is increasing at a rate of 4% per year. If there are currently 6,000 residents, about how many residents will there be in 5 years at this growth rate? Okay, so lots of things, populations, so we just saw populations, round elimination, bank accounts. Those are all exponential equations. Every time you see a percent or the words quadruple or triple, those should instantly spark in your head, okay, this is more of an exponential situation. Things are changing really rapidly here. This isn't a constant $15 an hour, right? So this is an exponential situation. Let's go ahead and highlight that important information. Population of small town is increasing, that's important, at a rate of 4% each year. And you know what? Increasing at a rate of 4%, and then we'll do per year as a separate one, right? Because that sounds like a time period. It's currently, that sounds a good word, about 6,000 people. How many residents will there be in 5 years? So it's increasing at this rate, right? That keyword, rate, should automatically spark which variable that is. Per year, sounds like a time period. Currently 6,000, maybe starts here. And how many will there be in 5 years? So let's see if we can take that information and create an equation. So we've got increase 4%. It's going to be per year, right? Currently 6,000. How many we'll say after 5 years. Again, I whittled it down to 4 pieces of information. So each of these is bound to be part of my 4 variables, right? So I have to think about which one's which. Let's start with the question. How many after? Is that an initial amount, a final amount, a rate, or a time? That sounds like a final amount to me, right? How many after 5 years? So this would be y. We are looking for y. Okay, cool. So we should be able to find a, b, and x. If that's not the case, then we can't solve the problem, right? Because you can only solve one variable at a time. So we should be able to find initial amount, rate, and time period. Let's start with our generic format. We've got y is equal ab to the x, ab to the x, right? We know we're looking for y, so let's just keep it y. Let's see, starting amount. A is starting amount, so let's go look over here. Starting amount here, it doesn't say anything about like in the past it was 5,000, so it looks like our starting amount is going to be that currently. It is currently 6,000. So it's going to start off with 6,000 people. All right, that was A. Good to know. Initial amount. Now I've got two more to consider for B and X. Increasing at a rate of 4% or per year. Well, we mentioned 3 times that per year sounds like a time period. So this is just going to be per 1 year, right? So X over 1, or just X, right? You can think about it that way. Let's look, so that would be our X. Let's look at the rate. This must be our rate, our B. However, this sounds a little weird. Increasing at 4%. So let's think about what's really going on here. Starting off with these 6,000 people, are they only going to get 4% back? No, that doesn't sound right, because 4% of 6,000 is only 240 people. And if it's increasing, shouldn't it be going up, right? Shouldn't it be a bigger number than 6,000? Not 240. So it's not just going to be 0.04, right? Instead, it's going to be like the bank account. You get all of it back and 4%. So our rate here is actually going to be 104%. And this is where you see that equation that I was talking about earlier. You see this one, 104%. That's what that means, okay? So if you ever see this equation written down, that's just all, it's trying to give you a hint that you need to add 100 here. But we're smart people. We can do that logically. We can just think about it, right? So here we're looking for 104%. Our B is going to be 104%. Don't want to put it in as a percent. Want to actually move it over 2 decimal places and put 1.04 as our rate. 104%. Okay, so now let's actually answer the question. We have our equation. Fabulous. We have a beautiful exponential equation. Let's use it to solve the question. How many will there be after 5 years? We're going to take this, plug it in for 5. Notice it's in the same units per year, right? 5 years. Unlike that first problem where it was in months, we don't have to convert it. That's good. So we'll just go ahead and plug it in as we see. Purple. So y is equal to 6,000 times 1.04 to the 5 over 1, or just 5, right? And of course, I will take the exponent first before I try to multiply. 1.04 to the 5th is 6,000 times 1.2166 ... times that by 6,000. You end up with about 7,299.917, which doesn't really make much sense when you're considering a population. So when I translate back, I'll call it, let's see, round up, 7,300 people. That's how many people I'm going to see in 5 years. Translate back. Okay, so once again, same steps as a linear, right? Same steps. Read, pull out important information, write it down here, right? Decide which one is your variables. Set up an equation. Set up an exponential equation. Use said exponential equation to solve, and then translate it back into something that makes sense, right? So same idea as the linears. Go ahead and try out example number 4 yourself, and then we'll do it together in just a moment. Make sure you pause the video. Okay, so hopefully you had time to pause the video and try this out yourself. If you didn't, then, or if you chose to just sit there and do nothing, I guarantee you your homework will be, it'll be quite hard, guys. So I hope you didn't do that. Let's go ahead and read it, do it together in class, just to make sure we all got the right answer. Example number 4. You want to reduce the size of a picture to place in a small frame. You aren't sure what size to choose on the photocopier, so you decide to reduce the picture by 15% each time you scan it until you get the size you want. If the picture is 10 inches long at the start, how long will it be after 3 scans? Alright, some important information. The fact that we want to put it in a frame, probably not that much, but reducing the picture by 15% each time sounds pretty important. Starting, if the picture was 10, let's do 10 inches long at the start, right? So 10 inches to start. How long after 3 scans? That sounds pretty important. Alright, so notice I took that whole thing and I whittled it down to 5 underlines. So I've got reduce by 15% each time. Each time. Or each scan, right? 10 inches to start. And then the question is, how long after 3 scans? Alrighty, so we've got this picture frame, it's 10 inches long to start, and we want to reduce it by 15% each time. Taking a look at that question, how long after each scan? Well, the starting amount was 10 inches, therefore this must be talking about the final amount, right? So it does look like we're looking for y. Sweet. That means I must have a, b, and x. So I'll go over here, y equals ab to the x. I'll start filling in those pieces. I know I'm looking for y, so it's still y equals. A represents my starting amount, which is 10 inches. We'll come back to b in just a sec, but I know it's each time, so I don't have to worry about that. It's x over 1 or just x. X represents the number of scans, right? Each time I scan it. Now, B, let's see, reduce by 15%. Well, what's happening here? I'm taking away 15%, which means how much am I actually going to be left with? I'm not going to be left with 15%, right? That's the same thing as being left with 4%, right? I'm going to reduce it down. So I'm going to take that 100% and I'm going to subtract off 15%. So I'm going to be left with 85%. So my rate is actually 85, or 0.85. 85% left, right? So this B, looks like B is continually something we always have to think logically about. What rate are you really talking about here? What's really happening? Okay, so that's the part you really want to practice, because the other ones, finding a starting value, I'm pretty sure you guys can pull out information like that. But the B and the X, that's the slightly challenging part of exponentials. You have to really think about those. Alright, cool. So that ends up being our exponential equation. Let's go ahead and use it to solve. After 3 scans, so x is equal to 3, 10 times 0.85 to the third. 0.85 to the third is 10 times 0.614125 dot dot dot. And then that ends up being about times 10, that's 6.1425. So y equals 6.1425, which is great, but what does that mean, right? Y was the final number of inches, so we'll call the inches, y is, or not y, we'll say after about 3 scans, it's about 6.14 inches, which is 2 decimal places. 6.14 inches. We have our answer. Awesome. Okay. Example number 5. Let's keep going. As a science experiment, you are watching how fast bacteria replicates. You start with 8 bacteria in your petri dish. If you know that bacteria triples in 4 hours, what equation can be used to model your petri dish? How many bacteria will you have after 4 hours? So they're actually asking us to come up with an equation this time. We have to make sure we have the equation. Let's start by underlining. Let's underline this bad boy. It's okay. We're interested in how fast bacteria replicates. Great, but doesn't really help us with the equation part. Start with 8 bacteria. That sounds pretty important, right? Let's see if we can identify that right now. What variable do you think that would be? What do you think? All right, you guys have some opinions. We'll have to see in a sec. If you know that bacteria triples in 4 hours, interesting. Wonder what those could be. What equation can be used to model your petri dish? How many bacteria will you have? Okay, so how many bacteria after 24 hours? Interesting. Okay, so let's break that down. Starts with 8. right? We start with 8 bacteria, so we'll call it back. Triples, that's one of those keywords, right? Any percents are keywords. 4 hours, every 4 hours. And then how many after 24 hours? All right. So I've whittled my information down into 4 important pieces, 4 important facts, right? I've whittled this whole situation down to 4 important facts. The question itself is asking how many after, right? Sounds like a final amount, right? Same thing as last time. How long after 3 scans? How many after 24 hours? So this is going to be our y. Looks like we're looking for a y. Like I said, 9 times 10 it is going to be a y, but sometimes, as you saw, we are looking for other things like a, right? Or b or x. But here we are looking for y. So we have y is equal to ab to the x is our general form. Nice general form. And we know we're going to still be looking for y. Alright, A starts with initial amount, so that's pretty easy to find. Bacteria, 8 to start with. 8 bacteria to start with. Triples means what? Like triangle. Triples means 3, so that's our rate of 3. And we're not tripling, 5% or reducing by 16, so this one's actually pretty straightforward. So if you see words like that, you should breathe a sigh of relief because those are pretty straightforward. Half, triple, quadruple, doubles, right? Those nice easy words usually just generate to just straight numbers, right? It's the percents that you really have to think about what's going on. But it looks like our time period is not quite every hour, right? It's not each time or per year. It's every 4 hours. So it's one of those weird situations again, right? So let's think about this. If I want to know about 24 hours, how many times is it actually going to be tripling? Well, it's going to be tripling, let's see, first in 4 hours, then at 8 hours, then at 12 hours, then at 16 hours, and then at 20 hours, and then at 24 hours. That's going to happen 6 times, okay? So my equation should change the exponent to 6, right? Otherwise it wouldn't be happening in every 4 hours. It would be happening, and we want it to happen 6 times. So what we're going to do is take this, right, we're going to take this guy, and make it x divided by the 4 hours. That way, no matter how many hours we plug in, it'll divide, right? And then we notice that if we do that to our 24, we end up getting the 6 times that we need. Sweet. So that's kind of how you can tell how you should adjust it. Think about it logically, right? Think about what's actually happening. Do it yourself, then adjust it in the equation. All right, we have our equation. There's the first part. Now let's use it to solve how many bacteria there will be after 24 hours. So we're still looking at y. 8 times 3 to the 24 over 4 hours. Plug that in. Okay, start with that exponent. We'll simplify that guy. That becomes 6, just like we wanted it to. 3 to the 6th is 729, right? PEMDAS says I have to start with the exponent first. So this is not 24 to the 6th. Not 24 to the 6th. It's 8 times 729. Times 8. We end up with y is equal to 5,832. 5,832. What does that mean? That means after 24 hours, we have 5,832 bacteria in our petri dish. That's very fast. Hope we have a big petri dish, right? If we started out with teeny tiny 8 little bacteria, and then after 24 hours, all of a sudden it's 5,000, that's why people get sick, right? That's why you don't want to eat food that's gross, right? 2 days past its expiration date, you're already looking at 5,000, or a day past its expiration date, you're already looking at almost 6,000 bacteria, right? So don't eat expired food is what you should take away from this problem. Hopefully that makes, or if you have any questions, make sure you pause the video. But as you can see, it makes a lot of sense, right? What parts do you need? Plug them in, solve. Cool. We're going to do one more today. One more today. Example number 6. Let's get at it. On opposite sides of a major city, 2 suburban towns are experiencing population changes. Town A, is growing rapidly at 5% per year and has a current population of 39,000. Town B is declining at a rate of 2% per year. Its current population is 55,000. Economists predict that in 5 years the population of the two towns will be about the same, but the residents in both towns are in disbelief. The economist also claims that in 10 years after that, Town A will be double the size of Town B. Can you verify these predictions based on the data given? Do you think these predictions will come true? Okay, so much information there. Lots of stuff to deal with, right? 2 whole towns of information. So let's not have our eyeballs pop out of our head. Let's just underline. Let's just underline. Forget about exponents for just a sec. All right, opposite sides, 2 major suburban towns are experiencing population changes. Not the most important thing right now. In one town, Town A, I'll even go so far as underlining in different colors. So Town A is growing at 5% a year. Its current population is 39,000. Okay, that's Town A. Let's use blue for Town B. Town B has declining population at a rate of 2% per year. So declining, that's important to think about. Its current population is 55,000. Alrighty. Let's deal with situation number 1. Economists predict that in 5 years, the populations of these two will be about the same. So that's the question. Will the populations of these two in 5 years be about the same? Right? That's what he predicts. We're going to see if it's true. And then the second question is he says in about 10 years, Town A will be double the size of Town B. So there's actually 2 things here. Can you verify these will come true? And can you verify these predictions based on the data? Do you think they will come true? All right. So we've got 2 separate things here. Now, here's the thing. Since they're asking 2 questions, I could make 2 different problems, but that's a waste of my time. If these are the same towns, right, in both questions, I'm going to make equations and then plug into them twice. That's the point of an equation. For example, if I wanted, like back in the last problem, if I suddenly also wanted to know about 2 days, 48 hours, I don't need to start the whole problem over again. I can just use the same equation. So if you make an equation the first time, instead of just counting, you don't have to keep counting. You can just use the equation again. So let's make an equation for Town A and an equation for Town B. Okay? So let's start with Town A. I have like very little room here, so I might not write things down. But we know it's growing at a rate of 5% per year, right? So we know growing, growing at 5%. Wow. Yeah, I'm not going to write things down. Sorry, mine is a little squishy. So Town A is growing at a rate of 5% each year. Current population of 39,000, right? So it doesn't say anything about the final amount. We'll call it Y. Current population, starting population, 39,000. That would be our A, right? By now, we can hopefully pick these out. Otherwise, you're welcome to come in, get some questions answered, things like that. The rate we have to be careful about, but it's per year, so it's just to the x. Per 1 year, so over 1x, right? So over 1. All right, now that rate, it's growing, so adding a 5%, right? 0.05. So it's that situation where we have 100 of the people, that's all 39,000, and 5% more. So it's going to be 100% and 5%. That's going to be 1.05. 105%. All right, we came up with an equation for Town 1. Fabulous. I'm going to let you guys try out Town B. Okay, so look at it carefully. See if you can come up with the same type of equation for Town B. Pause the video if you need time. Alright, so I hope you had some time to try this one on your own, because it's virtually the same. And if you're not trying, again, I can't help you. But let's check this out. So Town B, again, starts with Y. This one has a current population of 55,000. The rate is also per year, right? So it's just to X. Excuse me. But this one is declining. That takes away 2% or 0.02. Right? So if we're taking away from the population each year, it's supposed to be going down. So we're not getting the full 100% back. So it's 100 minus 0.02 or 0.98. All right. And we have both equations. Sweet. All right, now that we have both equations, let's answer the purple question. In 5 years, will they be about the same? So in 5 years, let's plug in 5 to both. 5 years, y is equal to 39,000 times 1.05 to the 5th. That equals about 49,775, we'll round, people. And then on the other side, in 5 years, hopefully they're about the same. Times 0.98 to the 5th. So 0.98 to the 5th is about 0.903927 blah blah blah. Times that by 55,000. We end up with 49,716 people. And take a look at that. For a town population, I would say, yeah, that's pretty close. That's only like 50 people off. So I would say this economist is pretty right. In about 5 years, both of these equations spit out about the same number, or in about 5 years, they've got the same population. So check, we can verify that one. Let's also verify that in 10 years, he says that the town A will be double town B. So let's take a look at that. Let's plug in for town A. Y equals 39,000 times 1.05, this time to, the 10th. That's going to equal, let's see, 1.05 to the 10th times 39,000 is 63,527. Round up, right? Round 7. And then town B is going to be 55,000 times 0.98 to the 10th. 0.98 to the 10th times the 55,000 is about 44939. Alright, that's a little more interesting. I don't know if I believe that one, right? Double of this, so double of town B would either be town A should be around 80,000, 82,000, 88,000, or town B should be around 30,000. So I don't know if I believe that one. I don't think that town A will be double the amount of town B, right? See what I mean? So let's say probably not that one. I don't think about that one. So we'll say yes, they will be about the same, but no, they will not be about the same. Or they will not be double in 10 years. Notice how easy that was to find, how easy it was to answer both questions because we had equations. If we didn't have equations, we'd have to sit here and count it out over and over and over again. We'd have to count 5 more freaking years, and that would be way too much time. For 2 different towns, too, that would be so many calculations. The fact that we made equations made it very easy to solve for both, almost virtually at the same time. Alrighty. So, that's creating exponential equations. We talked a lot about context today, but it boils down to the same things you'd find in linears. Underline, pull out information, make an equation, use it to solve. We talked about how you would adjust your rates, how you might adjust your time periods, right? Some examples of that happening, and then we used it to answer some questions. If you have any other issues, questions, comments, concerns, then you can either ask the sub, come ask me. Remember, you've got after school, before school, tutoring, engagement time, or I said before school, advisory time. You can email me. I can try my best to do it over the email, totally fine. I'm pretty good at syntax on the email. So yeah, you've got options to get help. Do not think you're just sitting here, messing around. Make sure you get this done. If you don't have any questions, though, you may begin your homework, and I will see you next time.